Now let's discuss about the functions which are required for implementation of AVL tree. So the first and foremost important function here is insert, that is taking two parameters. First is of type node star and second is value that we want to insert in AVL tree. So once the value is inserted, it will also return the pointer which is of node star type. Okay, so let's take some values as a input values and see how this AVL insertion code will work. So first value to be inserted here is 55. So let's see 55. So initially value of root equal to null. Yes, this condition is satisfied. So it will come in the if block. It will allocate memory for this AVL node just like we used to have nn equal to new node. In the same way here we have taken variable as a root instead of nn. So root equal to new AVL node. So AVL node is a name given to the structure. And then we know the value will be copied into root dot data, and as a good practice we always set its left and right pointers to null. So root dot data will be equal to value that is passed by the user from main, and then root dot left and root dot right will be set to null, and it is returning value of node star type, so here it will return the root. Okay, and yes, so node is allocated and it is inserted in AVL tree, so it will not come in any of the else part and it will directly return this root. So now root is pointing to 55. So please try to understand how the code works for different insertions. Now the next value is to be inserted is 25. So it will come again in the insertion function. So here root is passed. So we have root which is currently pointing to 55. Then now we have to insert 25. So it will check if root equal to null. No, now root is not null. It is pointing to 55. So it will come in the else part and will check whether value to be inserted, that is 25, is less than root dot data. So 25 is less than root dot data. Oh yes. So it will come in this else part and it will again give recursive call to the insert function. And now see which are the parameters passed: root dot left comma value. Now what is root dot left? For us there is nothing at root dot left, so ideally this is null, and 25 is passed. So recursive call will again go in insert function, and now here you can see root dot left will be copied in root when it is invoked for second time, right? So now root dot left is copied in root and now root is null. Yes, so it will allocate memory for this 25 and it will return the root. Now you can see where this return value is getting copied. It is getting copied into root dot left. So now root dot left is pointing to 25 and we can see here balance function is called on root. Okay, so who is root of 25? Root of 25 is 55. So please try to understand here is that when we perform insertion, balance function is called for the parent node of the newly inserted node. So for us 55 is parent of 25, so it will call balance on 55. So when we call the balance function, already we have seen what is happening in the balance function. Now the node passed here is 55. So now it will give call to different function diff by passing the 55 as a temporary node. So what this difference function is doing, we can clearly see in difference function what it takes that node as a parameter, and then again it is giving call to the height function, height on temp dot left and height on temp dot right, and again it calculate balance factor as left subtree height minus right subtree height. Okay, and what this height is doing, already we have seen how height works. So it will return the maximum height of the tree, whether it is like if left subtree is we can say longer, or if there are more branches on left subtree, then it will return left subtree as a max height, or else it will return right subtree as a max height. Okay, so this is height on temp dot left copied in L height, height on temp dot right copied into returned into R height, and how max height is calculated then, the one who is maximum out of L height comma R height will be returned as max height, and then we add 1 to it, because we know generally we consider root at level 1 level 0. So in order to calculate the complete height we just add 1 to it. Okay, so that's about height. Height will return you whether left branch is heavy or right branch is heavy. Okay, and then what this difference function is doing, once you get the height of left subtree and right subtree, it will find out their balance factor by subtracting L height from the R height. Okay, and now this balance factor is returned to the insertion function, and where it is returned? Here. Okay, so balance factor is returned over here to the balance function. Now yes, there are some interesting things when we are dealing with AVL tree, that we have to deal with the balance factor. And we know that if the node has balance factor as 1, -1 or 0, there is no need of rebalancing by calling the rotation. But if balance factor, if it is greater than 1 or less than -1, okay, or if it is anything apart from 1, -1 and 0, then we need to have some types of rotation. Okay, so here we can see if balance factor is greater than 1, if it is greater than 1, it means of course tree is heavy on the left hand side. And if it is less than 1, it means that tree is heavy on the right side. Because we know when the tree is left skewed, of course the balance factor will be positive. And when tree is right skewed, the balance factor will be negative. But again, there are two cases in left subtree and two cases in right subtree as well. So if balance factor is greater than 1, again we check. If difference, we call difference on temp dot left, if it is greater than 0, it means it is LL type of rotation. Hai. If difference on temp dot left is greater than 0, it means it is LL type of rotation. Left's left node is inserted, and that's why tree has become, or the node has become critical. Okay, if difference on temp dot left is greater than 0. But if it is less than 0, it again means it is LR type of rotation, which means that the new node is inserted on left branch's right side, and that's why the node has become critical. So even though balance factor is greater than 1, for left subtree, two options will be there, two types of rotation, LL and LR. And when balance factor is less than -1, it simply means that tree is right skewed, tree is heavy on the right side. And again, just like left subtree, there will be two options in right subtree as well. And which are those options? RR and RL. So if difference on temp dot right is greater than 0, it means we have to perform RL type of rotation. And if it is less than 0, then we have to perform RR type of rotation. Okay, so this particular function, balance function, it calculates balance factor, and additionally it also decides which kind of rotation is to be taken. Okay, which kind of rotation is to be taken? Is it LL or is it LR kind of thing? We can see here, here it is LL of rotation. And if we call the difference function on 25, so the balance factor returned here is 2, right? The balance factor returned here is 2, and that's why we came to know that here we have to go with LL type of rotation. Okay, and similar thing we can relate for RL and RR type of rotation as well. Okay, so what this balance function is doing? Calculating balance factor, and it also decides which type of rotation is to be taken. How we decide which type of rotation is to be taken? We find out where newly inserted node is, where we have inserted new node. Why? The parent node of new node is becoming critical. On which branch, on which side we have inserted new node. If it is on left's left, we say LL. If it is on left's right, it is LR. If it is on right's right, then it is RR. And if it is on right's left, then it is RL type of rotation. So I hope you got the idea about this balance factor function. Now again, coming back to the insertion. So we have seen for when we insert 25, balance factor will be calculated for its parent node, that is 55. But yes, the balance factor here is 1 because we have got the left child at level 1, but there is no right child. So at level 0, 1 minus 0, balance factor of 55 is 1, and so there is no need of rebalancing, right? Okay, let's moving next, we have to insert 65 here. So again, insertion will be called by passing root and value as 65. So if root equal to null, no, root is not null, it is pointing to 55. So it will come here in the else and we'll check whether value to be inserted is less than root. No, value to be inserted is not less than root. Is it greater than root? 65? Yes, it is greater than root. So it will come here in the third else if block and it will now again call insertion function by passing the arguments as root dot write comma value. Now root dot write, there is nothing on root dot write. So for now it is null and value to be inserted is 65. So what will happen? Yes, root dot write is null. So yes, memory will be newly allocated for 65 and its left and right pointers will be set to null and it is returning the root. So where this root will get copied? Root will get now copied into root dot write. So in root dot left we have 25 already inserted and just we have inserted 65 and now who is pointing to 65? Root dot right is pointing to 65. And again it will call balance function on whom? I already told balance is called for the parent node of newly inserted node. So who is newly inserted? 65. Who is 65's parent? 55. So balance will be called for 55. So we have only one parent, otherwise the balance function would be called for parent's parent, parent's parent, parent's parent unless we reach to the root level. So remember that after every insertion, we have to calculate balance factor for every node that belongs to your AVL tree. Okay. Now the next node to be inserted here is 9. So where 9 will be inserted? We already know root is not null, whether it is less than root dot data. Yes. So it will again call insertion function by passing root dot left as a next parent. So who is at root dot left? 25. Okay. So 25 comma 9. And again insert will be called on root dot left. 25 comma what is value to be inserted? Value to be inserted is 9. Okay. But root dot left, it is not null. It is 25, right? And what about the value to be inserted? That value is less than 25. 9 is less than 25. So again insertion will be called on root dot left. So 25 left is nothing. It is null. So memory will be newly allocated for 9 and 9's left and right we set as null. And who is now your parent node for 9? Parent node for 9 is 25. Okay. So now root will be pointing to 25 and now again balance function will be invoked on 25 because 25 is parent of newly inserted node, no? Right? Okay. So when we insert 9, balance will be called on 25 and balance function will be also called on 25's parent, that is 55. But we can see here, though it is called for 25 and 55, in all cases tree is balanced and there is no need of any kind of rotation. Now let's move to the next number to be inserted, that is 8. Now already we know how this code is getting executed. So we know where this 8 should be inserted. It is smaller than 55, smaller than 25, smaller than 9. So it must go on root dot left, that is 9's left. Okay, so 8 will be inserted over here. But now when I insert it here, we can see the balance factor of 25 drops to 2. Why? Because 25 has, you can see 2 nodes are there on the left side, but no right child here for 25. So the balance factor will be positive as this seems left skewed tree. So 2 minus 0, right? There is nothing on the right. So balance factor of 25 will be 2. So now here we say that 25 has become critical node because it has violated the property of balance factor that AVL tree belongs to 1, minus 1 and 0. Now the balance factor of 25 is 2. So what should we do? First of all, we should identify. We have seen what balance function does. It calculates the balance factor. So it has already returned balance factor that is greater than 1, right? So balance factor is 2 here. So that is already returned by balance function. And in addition to that, balance function is also telling. So in balance factor, what is returned? 2 is returned. It also finds out why the node has become critical, right? Which kind of rotation it is, isn't it? So here you have to see if balance factor is greater than 1. So it is 2. Yes, it is greater than 1. Again you have to check inside if difference of temp dot left is greater than 0. Okay. difference of temp dot left is greater than 0, right? So yes, it is greater than 0. So it means which kind of rotation we have to take here? Here we have to take LL type of rotation. Now let's go to the code where we have defined this LL. Now what is LL rotation? LL is left rotation. So rotating tree towards the left side is called as LL rotation. Right? Now let's see this figure where I have solved this example manually. So we know if it is LL rotation, what we do? We rotate our tree towards the left side. That is, we are rotating the tree clockwise. And if I fold this tree clockwise, what will happen? 9 will become the root, 8 will become left child, and 25 will become the right child. Isn't it? 25 will become the right child. And 65 will remain there as it is. Okay. So let's see the nomenclatures which we have used here in LL rotation, left rotation. So you can see what we have done. We have taken one temporary variable. So we know the rotation function. Okay. Here the LL rotation will be, balance function is called on whom? Balance function is called on parent node. So that is same thing which we pass to the LL rotation. So here we have passed 25 only. Okay. So here parent's left node. Who is our parent node? 25. Parent left node. Who is parent left? 9. That we temporarily copy here in the temp variable. Okay. Parent's left is copied into temp. Why? After rotating the tree, the parent node will go into temp's right. Remember. Because see, just imagine if tree is rotated towards the clockwise. If tree is rotated clockwise, what will happen? 9 will become the root and 25, who was parent, will go on right side of 9. Here you can see here in the figure. What is that? The parent node of temp is now on the right side of temp. Okay. So see what we have done in step number 1. Parent left is temp. So parent left. Who is parent left? 9. 9 is our temporary node. Then what we do is temp's right. Now if we look at our problem, there is no one on temp's right. But if it is there, so I have just shown here like in a dotted line. If someone is there on the temp's right, say for example 10. Now this 10 value is smaller than your parent na. So that will go on the left side of parent node, right? So if at all someone is there on temp's right, that you copy to the parent left. Okay. So here we can see here clearly. Consider if 10 would have been there on the right side of 9. Okay. 10 would have been there. Now 25 left branch contains the 10. So after rotating the tree, 10 will go on left side of the parent node, right? So here what we have done, temp dot right, that is this value 10. Where it is copied? It is copied into parents dot left because it is smaller than parent, right? And after rotating the tree, this temp dot right will go in the left part of parent node. So here we can see temp right is copied into parent left. Okay. And where this parent node will go? Just rotate the tree clockwise. What will happen? 9 will become the root, 8 will be the left child, 25 will be the right child. And if 10 is there, then we have already copied it. 10. Where? Temp right we have already copied into parents left. So here 25 was parent and 10 is copied here in the parents left. I hope you have understood this LL kind of rotation. In LL what we have done? The node which became critical or for which balance factor is more than 1 is considered as parent node. Then parents left is taken into temporary. Okay. If anyone is there on temp's right, then where it will go? It will go on parent's left. Because that will be smaller than parent node. Na? It is lying in the left branch of parent. It means it is smaller than parent. So after rotating the tree, if the 9 will become the parent and if parent has some child, where it should go? Right? So it will go on the parent's left side because it is smaller than parent node. Right? And fine. And where parent will go? Yes, parent is inserted as a right node to the temporary. So here we can see 25 which was parent earlier will become now right child of this 9. Right? Okay, so this is how LL rotation takes place. In a very similar way, RR rotation takes place. Just instead of parent dot left in RR, you will have parent dot right. And here instead of temp dot right, here it will be temp dot left. And the parent node will be copied into temporary dot left. Here it was copied into temporary dot right. So just in left rotation, where we used left, it will be replaced by right, and vice versa in case of RR rotation. I hope you have understood this LL and RR. Now moving next, we have to insert another number, that is 15. So where 15 will go? Now this was our figure after performing LL rotation. Consider in a same figure here we are inserting this 15. Okay, but now after inserting 15, what will happen? 25 will become critical. Why? Because 25 has two child nodes on the left side, but there is no one on the right side, right? So 25 is our parent, right? And now what will happen? As this node has become critical, the balance function will immediately tell you why this node has become critical, because of whom. 25 became critical because of 15, and where 15 is inserted? On the left branch right side. So which kind of rotation it is? It is kind of LR rotation. Now I hope in theory you have understood how this LR rotation takes place. We have already seen LR means when it is LR, you have to go from right to left. It means what? Rotate the tree towards the right side first. That's what we say, that convert it in LL first. So if I want to convert, you take rotation first, you will convert it in a kind of LL structure. So what will happen? 15 will be rotated towards the right side. So 15 will become root, and 10 will be attached as a left child of 15. Right? So now we know which kind of rotation it is looking like. It is looking like L type of rotation, right? And we know how to resolve LL. Just we have seen like this code we use for resolving this LL kind of rotation. So see, what is the code for LR rotation? The code is passed here. 25 will be passed because 25 has become critical node. Okay, so this is what 25 will be called as a parent node. So parents left, who is parents left node? 10. Parents left node is 10. So what you will do? You will perform right rotation on 10. So if you rotate this 10 towards the right side, who will become parent? 15 will become parent, and then 10 will be attached as a left node of 15. I have already told you, right? So when you are resolving LR, first of all, you will call RR rotation, that is rotate the node towards the right side, and then call LL, because see, you can clearly see here resolving LR is to the LL kind of structure by taking right rotation first. And once you take right rotation, then you will give call to LR rotation. And how LR will be after rotating tree towards the right, you will give call to the LL rotation. And how rotation is done, that's we have already seen here, right? So this is what, after taking rotation, then you have to deal with LL. So what will happen? If you want to take LL rotation here, 15 will become parent node, 10 will go on left of 15, and 25 will go on right of 15, isn't it? So how your tree will look like? 55, left 9, right 65, and here the place where we have taken rotation will look like this, where 15 is parent, 10 on left side, and 25 on right side. Okay, so in very similar way you can do RL rotation, in which we take left rotation first. You can see RL, always you have to go in a reverse way, like RL, you have to rotate your tree to the left side first and then call RR rotation. Okay, rotating tree towards the left and then calling RR rotation. So this is how we resolve RL rotation as well. So I hope with this we have discussed about 4 types of rotation. With insertion function, insertion is written as a recursive code where it will be recursively called by finding appropriate place for node to be inserted. That is whether the new node will be inserted on roots left or roots right based on the values where they are greater than the root or smaller than the root. And then after performing insertion, it will call balance function for the parent node of the newly inserted node. So balance factor will be also recursively called for parent's parent in the upward direction unless we reach to the root and we ensure that the balance factor is not critical for all the nodes. Okay. So this is how all kind of rotations are taken. And now the last function remaining here is for displaying the tree. So how do we display the tree? So very simple code is written for displaying a tree. So it takes root and level as two parameter. So if this root past is not null, so what we are doing first, we are showing the right node first, okay, the right child, and then followed by root, and then followed by left child. Okay, so the right value, then root, and then left value. And how the differentiation is made between left and right, so we are keeping proper indentation here. You can see this cout is putting indentation over here. Okay, so you can see even though printf is used, it's okay that we can have a mix of cpp and c as well. So even though we put printf, ideally it should be cout, but yes, this program will be executed even if we write it in this way. Okay. So this is how the AVL tree can be implemented. I will also show you on online GDB here how this program is implemented. So let's see. We will give same input as that of the problem which we have solved. So you will come to know about this. So 1, the value to be inserted is 55. 1, the value to be inserted is 25, and 1, the value to be inserted is 65. See, the output here is, you can see here, the root value is, okay, now we'll call display function to see who is root. 55 is root, left node is 25, and the right child is 65. So the right child is displayed first, followed by root, followed by left child. Again I call this insertion function, and the node to be inserted is 9. Again I call insertion function, and node to be inserted is 8. Again I call insertion, and node to be inserted is 15. And let's call display function and see the output. See the output. Now try to relate it with this. Okay, so we can see the right nodes are displayed first, followed by the left values. Okay, followed by the left values. So this is how program for AVL tree can be implemented. Thank you.